Omic and multi-omic approaches can simultaneously access some 1,000 molecules, measuring their concentrations with an accuracy of a few percent. This information comes in the form of about 1,000 two-digit variables. Vibronic electric field molecular fingerprints may deliver many thousands of 5 to 6-digit variables. In order to exploit this potential, the fingerprint variables must carry independent information. In a native biological sample, many of them may be correlated due to overlapping spectral features and due to signals from the majority of molecules being covered up by those from several high abundance analytes. Both problems can be mitigated by isolating the fingerprint of small groups of molecules, either by physical separation via liquid chromatography or by exploiting the longer-lasting molecular response that follows electrospray ionization, or possibly by a new approach yet to be discovered. The multi-digit accuracy of the measured fingerprint variables can be exploited for medical applications only to the extent permitted by biological noise. The molecular composition of blood varies from person to person, even among healthy individuals, partly due to the dependence on personal covariates such as, for instance, age, gender, body mass index, genetic information, all of these contributing to a combined outcome, a so-called phenotype. Populational studies will allow us to establish covariate ranges with the fingerprints of healthy individuals being nominally the same. For any given set of covariates, the residual between person uncertainty defines the normal range for molecular fingerprints. The narrower this baseline, the more precisely healthy phenotypes are defined, and the smaller the changes in the fingerprint that can provide early alert about an unfolding abnormality. Narrowing the baseline of phenotypes is therefore as important as improving fingerprint metrology. The discovery of all covariates affecting the fingerprint in a systematic way would yield the ultimate residual baseline of any phenotype in a given population. But even beyond that, there is a way forward. By monitoring the fingerprint over time in so-called longitudinal studies, the resultant within-person uncertainty in variation of the fingerprint over time may be even smaller than the ultimate residual between-person uncertainty. Establishing personalized baselines may thus open new avenues of phenotyping with an accuracy previously unattainable. To this end, we are collecting and analyzing as many human blood samples as possible with ever-improving fingerprint metrology, signal processing, and machine learning algorithms.